Welcome to another episode of Heat Treat Radio. Today we're going to be talking about case hardening and the hardenability of materials with our friend Michael Mouilleseaux from Erie Steel Treating in Toledo, Ohio. This is part two of a two-part series dealing with the hardenability of materials. In part one, we took a deep dive into reading a hardenability chart. If you'd like to access that episode, you can go to heattreattoday.com/radio and look for episode number 112, How to Use a Hardenability Chart. That's the name of it. So it's episode 112 at heattreattoday.com/radio. But for now, let's jump into a more comprehensive conversation about the hardenability of metals and especially the effect of core hardness on effective case depth. So with that, here we go. We're going to start talking today about pretty interesting topic, which it's got some interesting terminology that goes with it, but it has to do with hardenability, right? Hardness and hardenability of metals, which for people who don't know are not metallurgists and things of that sort, it seems like a strange topic because isn't all metal hard? But we're going to talk more about a little bit more in depth about hardness of metal, hardenability of metal, and effective case depth. What we want to do is just run down through this presentation on the influence of core hardness on effective case depth measurements. So, Michael, we are open to learning here.
So we're going to get a little bit into the weeds today. And in that, we're going to talk about some things specific metallurgical. So those that are involved in high volume production, carburizing, we know that consistency of results is extremely important. Not just important in that we have the process centered and that the results are that way, but ultimately it has something to do with the dimensional control. So specifically with gears, if the output from the process is not consistent, then one of the things that's going to suffer is going to be the dimensions on these things. So we're going to be talking about effective case depth today. And effective case depth is a little bit different from total case depth. So total case depth is the total depth that carbon is diffused into a part. And that's very much a function of time at temperature. And are there some nuances with grain size and alloy content? And there are, but essentially it's a time at temperature phenomena. Effective case depth, on the other hand, is a little bit different. Effective case depth, and I got a little graphic here to look at this. So if we look at this graph, the x-axis is we go to look at it to the right, it's the distance to the surface, and the y-axis, as it goes from the horizontal up, is hardness in Rockwell C. So if you look at this green line, this is a micro hardness traverse of a carburized part. It tells us many things. So you look at the left-hand side of this thing, 5, 10 thousandths in depth, and the hardness there is 60 Rockwell C. Then as you can see, it diminishes as we go further into the part, 10 thousandths, 20 thousandths, 40 thousandths, 50. We get to the end of that line and we see that's the core. So the core of that is a function of the material hardenability. So what is the effective case depth? So if we look at the second line from the right, it's a vertical line, blue, it says total visual case. So that's exactly what that is. If we were to look at this part and etch it, I'm presupposing that everybody understands that we would section a part, we would mount it, we would polish it, and then we would look at it under a microscope. At 100x, let's say, if we would look at this after it's been etched, we would see a darkened area, and that would be the total depth of carbon diffusion into the part. So that really is not a function, as I mentioned before, it's not a function of the material grade, essentially. As I said, there are some nuances there. But the effective case depth, that's a measurement. And that measurement here in North America, SAE standards, J423, we say that we measure the effective case depth to Rockwell C 50. So you look at the surface hardness is 60. We measure the hardness in increments. And when we reach this hardness, the depth that hardness achieves 50 Rockwell, that's the effective case depth.
Okay.
So again, if we look at the core hardness on that part, we can see that on this particular sample, it's somewhere between 45 and 50. So what is it that causes this core hardness? So it has to do with the hardenability of the material. So here we're looking at a SAE chart, J1268. It's for H-band material, for 4320, common gear material. This thing tells us a lot. It's got the chemistry on it. It has some information for approximate diameters. And then it has on the right-hand side of that, we're talking about cooling in water or cooling in oil. And then there are the surface, the 3/4 radius, and the center. So if we look at the surface, it an oil quenched at 2 inches, the surface at that, it has a distance from the surface of something like 4 or 5. So if you go over the chart on the left-hand side, you go to 4, 5/16, 29 to 41. So even though this is a hardenability guaranteed material, for a 2-inch round, you would expect to have something between 29 and 41 for the surface hardness. But now let's look at what would you get at 3/4 radius. So you drop down just one box there and you look at J2, you look at 2 inches and the geometry position there is 9. So you go back there and you can see that at 3/4 radius, so on a 2-inch bar, that's an inch and in 3/4, I believe. The hardness there is going to be something on the order of 23 to 34. In the center of that bar for a 2-inch round is going to be J12. So the J12 is 20 to 29. So that is the definition of hardenability. It's the depth that a material can be hardened. And it's totally a function of chemistry. Totally a function of chemistry. Davenport and Bain, they did the logarithms for this in the 1920s, in the run-up to World War II. So if we're going to evaluate what effect does the core hardness have, we're going to take and look at parts that are heat treated in the same furnace to the same cycle, in the same basket, under all of the same conditions, with the only thing being different is going to be the hardenability of the material. So we go all the way down to number 3 on this thing. The anticipated total case is going to be about 40 thousandths for all of these samples. So here's our samples. So we've got 5 of them that are on there. 4 that are on there. And if we look at the highest hardenability sample, the red line is what is the measurement of Rockwell C50.
Right.
The blue sample, which has the highest core hardness, also has the deepest effective case depth. And then as the core hardness is reduced, you can see that where the line crosses the plane of Rockwell C50, that is reduced as well.
So, for example, Michael, sorry, just to interrupt. So, for example, the yellow line here, which is the bottom line, it's
Yes.
got the lowest core hardness or hardenability, right?
Both. You're correct.
Okay. So that's why it's crossing the red line much earlier than the others are.
And it also has the lowest effective case depth. If we look at this in a tabular form, so this data, so how do we gather? What you looked at are microhardness traverses per standard using an MT90. The hardness was, the effective case depth was measured to Rockwell C. The total case depth was determined visually on these things. And you're going to see that, Michael, you've got 4 different materials there. And that is correct. That is correct. We also have 4 different hardenabilities. In answer to the question, if these were all the same heat, would we have these same results? And essentially we would, with the exception of the bottom one at 1018. There's no way that we could take an alloy steel and reduce the hardenability of that amount. So here's what we're talking about. They were all run to the same process. So how do we know that? We look at the total enrichment on this, and it's within the margin of error. It's 38 thousandths to 42 thousand. We look at the effective case depth, and interestingly, we have quite a variation there. So the first one, we have the highest core hardness. The core hardness is 46, and the effective case depth is 39. And then we have a sample where the core hardness is 44, and the effective case depth is 36 thousandths.
Mhm.
And then we have a sample where the core hardness is Rockwell C39, and we have 29 thousandths effective case. And then, of course, there's the 1018 sample that was put in there just as a reference. So the core hardness on that was 24 with 15 thousandths effective case depth. So is a direct proportion, that is, the core hardness, there's a proportion between that and the effective case depth that you're going to be able to achieve. So if we reference back to that hardenability chart that we looked at, if we look at a 1/2 inch section on that chart, so at the very bottom, a 1/2 inch section on the chart, quenched in moderately agitated oil, has a distance from the surface or a geometry position of J3. So if we look in the chart, we look at J3, you can see that what the range in hardness would be. So that means that at the lower end of the chemistry composition, we could have a core hardness as low as 35. And at the upper end of the chemistry composition, we could have a core hardness as high as 45. Let's go back and just visit that data. That column J3, that is the data that was provided to us by our customer from the steel mill. The steel mill, when they melt a heat of steel, this is a high value part. So they use what's called SBQ, special bar quality. Special bar quality is subject to a lot of scrutiny and a lot of controls. And one of the things that's provided, in addition to things like the chemistry and the internal cleanliness in the steel certification, is the hardenability of that specific heat. And so you can see that the 8620, the first slide, had a J3 of 44. We actually had a 46. So you say, what's that all about? So the way that you have to understand that you're going to melt 200 tons of steel, 100 tons of steel, whatever it's going to be. It's not all done at one time in a single pour. It's multiple pours out of a tundish. And what the chemistry and the hardenability numbers that you get in a steel certification is going to be very closely to an arithmetic average of what you would get when they test the first pours and the middle pours and the end pours. And they're going to average those things out. So internally, what we say when we're using this data is that we want to be plus or minus 2 points Rockwell C within the steel certified hardenability data. And I can say that, again, experientially over years, Gerdau, SDI, Nucor, the domestic sources of SBQ bar, they are very consistent in the way that they make this stuff. And this is something that we can depend upon. So if you think about this, you could use this as a check for what you're doing. So if the steel that you have has a hardenability of 44, and if you're not plus or minus 2, you have to ask yourself, why? There's only a couple of reasons that it would be outside those limits. So let's say that if it's above, it probably is not the heat that it's purported to be. If it's lower, it could either be not the heat that it's purported to be, or there could be an issue with the heat treating. And as I said at the outset, we're going to assume in this discussion that the reason that we have these numbers, the differential in core hardness that we have here, is not attributable to heat treating. It's solely attributable to the chemical composition of the material or the hardenability.
Yeah.
So what can we use this information for? So what we can use this information for is, if we're a captive operation and we are purchasing the material, you have an opportunity in defining in your purchasing practice what the hardenability of the material is going to be. As I mentioned before, the domestic sources are very consistent in the material that they produce. To produce a heat of 4320 that's got a J3 of 40 or 42 or 44, there's essentially, my experience, and I was involved in a major automotive supplier, experientially, There's no cost penalty to that. It's a definition of what you want. So they're not making heats in randomly selecting chemistries for these heats and selling them. They make a recipe for a specific customer, and that recipe, again, my experience has been that they hold very true to that. So if you think about it, just as with anything else, if you're introducing a lot of variation into your process, not only is it the output from that variable, but the cost of handling that is variable as well. A material such as this, to specify a J3 of 42 to 44, is something that is eminently doable. And again, my experience is that it's the steel companies have been able to do that over time with a great amount of consistency. Now, to those who are not involved in high volume production, where they do not have control of the source of the material, this chart remains something that is usable. So if you are running a job shop, let's say, or you're running shorter term things, and you don't have necessarily furnace load sizes of parts, then the key there is to be able to mix and match things into specific processes. At least in carburizing, if you understand what the hardenability of the material is, then you have a much better opportunity of taking multiple parts and putting them into a load and determining if you're ahead of time, whether or not you're going to have consistent results or not. So just one more thing that we'd like to look at here, and that is this next graph. So this is the Caterpillar hardenability calculator. So this is available from CAT. They readily share it with all of their suppliers. I have been involved in numerous businesses, and I've never been refused this. You have to ask them for a copy of it. But essentially what you do in this calculator is you input the chemistry of a heat, and it automatically calculates what the hardenability of that heat is. So what I've done here is, if you recall, the J3 on the 4320 material that we looked at, the hardenability guaranteed, that had a 10-point range. If you look at this particular heat, and this is what we call the open chemistry. So this would not be a hardenability guaranteed material. So what you have is the upper limit is higher than what you would see on a hardenability guaranteed material, and the lower limit is lower than what you would see. So the variation in a quote unquote standard SAEJ 403 8620 is going to be much wider. So the variation is going to be different. So if you look at that same J3 position, we're looking at 25 to 45, a 20-point swing in core hardness. If we go back and we just revisit the results that we had, 39 to 46 with a 7-point swing, we had a 10 thousandths difference in effective case depth. So if you had a 20-point swing, you could well imagine that is going to be significantly greater than that. So two things, again. One is, if you have the lower hardenability material, it allows you, if you have a lower hardenability grade of material, it allows you to modify your process ahead of time to compensate for the fact that the core hardness is going to be lower in this part. Vice versa, if you have an extremely hot heat where it's high hardenability, similarly, you would be able to say, I may be able to reduce some time. I would not have to put as much total case on the part in order to achieve what is specified as effective case. So the hardenability charts are great guides in helping you to establish a process and then to evaluate the consistency of that process. I'll just make one other comment about the chart, and that is, this is not a full-blown Lamont chart, which that is a chart which you have various quench severities for different sizes. And that can be utilized to help pinpoint this. As you can see on the SAE chart, you essentially have two different quench rates. You have mild oil and water. There are a lot of different types of quenchants that are available. I can tell you that moderate quench rate that's on this chart very closely mimics what experientially we've been able to achieve modified mark quenching. So I'm able to use this chart without any offset. So if you had, we do know that if you had a fast oil, petroleum-based oil, it was very fast. You may experientially, if you had a heat and you knew that it had a J3 of 40 and you're consistently seeing 44 out of it, then what you would have to say is that in your specific instance, that your quenchant is more aggressive than what this chart was built to simulate. However, you can continue to use the chart. It's just that you have to use your experience in doing it. So again, strategy to control it. The strategy to control it is getting the hardenability data so that you can utilize that ahead of time, taking that hardenability data and understanding what your specific heat treating operation is, more specifically, what your quenching operation allows you to achieve. And once you have that information, so you know that typically a section size of X in this furnace is going to give me a geometry position of Y. Then as you go forward, you can take that information and you can say over time, if I have a variation here, it's going to be an effective case step. Is that variation attributable to the core hardness? And if it is, there's a strategy to possibly change the purchasing practice and tighten up on that. If what is that it's attributable to something else, then that gives you very good information to say, there's something in my heat treating process that I should be looking at that's attributable for this variation in case steps. So we waded into the weeds and hopefully we have found our way out.
Yes, yes. No, that's good. That's good. Especially for those people who already know a little bit of metallurgy and know those charts. I think that explanation is going to be very good. So thank you very much for that. That's great. That's great.
I'm wondering, Michael, this is probably, I'm sure most of our listeners know this, if not all of them. But for in-house heat treaters, how often do they need to be aware of the material that's coming into their operations and to be testing it or be asking about the changes that could be happening to that material? Um,
So I would say that any heat treater that is worth their salt, to assume that the material does not come into play, hopefully this would give you reason to pause that. And the next thing would be, again, in high valued components, gears, shaft, power transmission, whatever it's going to be, those kinds of things, typically heat lot control is mandated by the end user. So if you have heat lot control, then you need the data that goes with that. And if you have the data that goes with that, utilizing the strategy that we just talked about, it's going to give you the ability of evaluating variation. So what is the source of, if the primary source of variation is the material, that needs to be addressed. If the material is very consistent and yet you continue to have variation, there's obviously something in the heat treating process that needs to be addressed to reduce that variation.
Thanks for listening, and thanks to Michael Mouilleseaux for presenting today. Appreciate your work, Michael. Give Heat Treat Radio a 5-star review or a like on Spotify, Apple Podcasts, SoundCloud, iHeart Radio, Podbean, or even on our website, which is www.heattreattoday.com/radio. That'll take you directly to all these podcasts. Let us know if you want to hear about any special topic on the podcast, or if you'd like to sponsor a future episode. You can let us know by emailing me directly. That's Doug@heattreattoday.com. And as always, this and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in part or in whole without advance written permission from Heat Treat Today. I'm Doug Gledd. Thank you for listening.